Hey everyone! Today we're diving into overfitting versus underfitting, two of the most important concepts in machine learning. Think of it this way, underfitting is when your model is too dumb to learn the pattern, and overfitting is when it's too smart for its own good and memorizes everything, including the noise. These aren't just academic terms, they directly determine whether your model will actually work when you deploy it in production. Understanding this balance is the difference between a model that gets 99% accuracy in your notebook and one that actually solves real problems. Let's break it down step by step. Let's visualize the machine learning training flow and where things can go wrong. We start with training data that flows into model training, where the model tries to learn patterns. From there, we have three possible paths. The underfitting path happens when the model is too simple, it can't capture the complexity, leading to high error on both training and test data. The good fit path is our sweet spot, the model is balanced and achieves low test error. Finally, the overfitting path occurs when the model memorizes noise in the training data, which looks great during training but fails miserably on new test data. The goal is always to land in that middle path. So how do you actually recognize these problems? Underfitting shows up when both your training and test errors are high. The model is essentially too simple to understand the pattern, like trying to fit a straight line through data that clearly curves. Overfitting is sneakier, your training error looks amazing, maybe 99% accuracy, but then your test error is terrible, like 70%, because the model memorized specific examples instead of learning the general pattern. Picture a student who memorizes answers to practice problems but can't solve new variations on the exam, that's overfitting. The goal is that sweet spot where you get a smooth curve that captures the real trend without fitting the random noise, giving you good performance on both training and test data. Alright, so you've identified overfitting, now what? Here are 4 powerful techniques to fix it. First, regularization adds a penalty for having large weights, which forces your model to find simpler patterns instead of memorizing details. Second, gathering more training data is often the best solution. It's much harder for a model to memorize 10,000 examples than 100. Third, cross-validation helps you test your model's stability by evaluating it on multiple different splits of your data. And fourth, if you're working with neural networks, dropout randomly turns off neurons during training, which prevents the network from becoming too dependent on specific pathways. These techniques are your toolkit for taming overfitting. Let me show you a concrete example with polynomial regression. We have 5 data points that follow a simple quadratic pattern. Now watch what happens when we use a degree 5 polynomial, way more complex than needed. We transform our features using polynomial features, fit a linear regression model to those features, and make a prediction. With only 5 training points and 5 polynomial terms, this model will fit the training data perfectly, but it's basically memorized those specific points. When you predict on new data, like x equals 6, you might get wild, unrealistic results. This is a textbook case of overfitting, the model complexity is way too high for the amount of data we have. Let's wrap this up with the key takeaways you need to remember. Underfitting means your model is too simple with high bias, while overfitting means it's too complex with high variance. Always check both training and test error. If someone brags about 99% training accuracy but won't mention test accuracy, that's a red flag. Think of that spam detection example, 99% on training but only 70% on test data clearly indicates overfitting. Use the techniques we covered, regularization, more data, and cross-validation, to find that perfect balance where your model captures real patterns without memorizing noise. Now you understand one of the most fundamental challenges in machine learning. Congrats, you're one step closer to building models that actually work in production.